From the drama of our planet's origins and the birth of our solar system comes one of the most startling revelations of modern science. The solar system we see today, quiet, stable, was once a battlefield. Newborn planets blasted through space, competing for stable, circularized orbits inside a grunge-style mosh pit of gas and dust. For those that find the right balance, the prize is survival. For the rest, world-shattering destruction. A new look at the chaos of creation and a frightening possibility in our distant future. Mars. The Curiosity rover is searching for clues about the origins of the red planet. It confirms the presence of oxygen and nitrogen isotopes hidden in the rocks and soil.
We use isotopes to try to figure out the history of planets, partly because they are immune to many of the changes, the chemical changes that occur when you have things like collisions and so forth. Isotopes, the relative abundances of these isotopes are like fingerprints.
Curiosity confirms a unique mix of isotope fingerprints. The isotopes indicate that Mars formed elsewhere in the solar system and moved into our neighborhood. Our solar system is full of oddities pointing to an imperfect birth and a malformed evolution. All of our planets go around the sun in the same direction that the sun is spinning. This is the same direction that the clouds within our original nebula began to rotate. 6 planets spin around their poles in the same direction. For them, the sun rises in the east and sets in the west. Yet 2 planets spin the opposite direction. For Venus and Uranus, the sun rises in the west and sets in the east. Uranus not only has a retrograde spin, it rolls on its side like a bowling ball. At Neptune, the icy moon Triton orbits backwards, opposite from the direction of Neptune's spin. Do these planets spin backwards because they were rocked by titanic collisions in the past?
So we see evidence in the architecture of the solar system for not only collisions, like Earth's moon, and the fact that Venus is rotating in the wrong direction, and Uranus is on its side, and so forth. All these things are attributed to collisions. We also see in the asteroid belt and in the Kuiper belt, the outer asteroid belt, if you like, we see that the orbits of these things look like they've been disturbed.
Closer to home, our own Earth has an inexplicable 23.5-degree tilt. Its spin axis is radically misaligned from its magnetic pole. And our moon is comparatively large for a planet our size. Now, a new theory may be able to explain many of these oddities. It is called the Grand Tack hypothesis. Four and a half to 5 billion years ago, a gas giant planet arose inside a primordial disk of gas and dust.
Jupiter didn't just form where it is, but formed and then moved inward towards the sun.
As it spirals toward the Sun, Jupiter herds asteroids and rubble.
Jupiter's natural tendency is to drift in slowly through this debris field that it's traveling around.
The inner solar system is also thick with gas and dust. The birth of our planetary system is well underway. Numerous worlds are born in this region, including the Earth. Primordial skies are ruled by chaos. Jupiter's approach destabilizes these planets. Their orbits decay into wildly swinging ellipses. Some are tossed out. Others fall into the Sun. Their numbers are unknowable. These are ghost worlds from a bygone age.
Jupiter just causes all heck to break out in the solar system, and all that debris in the outer solar system gets flung inward towards the inner solar system.
And it was a busy time in the very early solar system, and things were colliding with each other all the time.
And then it stopped. Jupiter's invasion of the inner solar system is mysteriously halted. The planet makes a turn, or, in sailors' parlance, a grand tack. Lurking behind Jupiter is a second gas giant, Saturn.
So as Jupiter was migrating inward, Saturn was following it and growing. And as Saturn was growing, it came to have a size that it had a gravitational impact on Jupiter, which became more important than the gravitational interaction between the gaseous disk and Jupiter. They reverse direction. And in a sense, you can think of Saturn and Jupiter feeding off one another and moving back out.
Gravity tugs each passing planet. This transfers orbital energy from one world to another.
All you have to do is exert a very subtle little periodic force at the right time, and you can have amazing changes in the motion of the object you're pushing on it.
Once enough energy has been transferred, the planets synchronize their orbits. They are said to be in a resonance. For planets, resonances are achieved and maintained through the mutual push and pull of gravity through the fabric of space. They're a key factor in the continuing evolution of our solar system. This effect can be duplicated in the lab.
We have 10 metronomes here set up on a swinging platform. They have little weights on pendulums here, but they've all been set at the same frequency. And I'm going to try to start them as best I can, completely out of phase, randomly. So their oscillation is going to transfer energy by the swinging of this plastic sheet to the other metronomes that are out of phase to get into phase with the majority. It's inevitable that there's going to be some majority group which starts out swinging more or less together, and they are eventually going to win out. Just doing this as randomly as I can. Aha, maybe in this corner I see 4 that are pretty closely synced. Yes, now it's more like 5, 6. Now you have one that's almost completely out of phase. So every time the majority hits a beat, it's going to give a little impulse, a little push to the platform, and that push is transferred to the metronome that's not in sync. Because the platform, you can actually see this platform vibrating back and forth in sync with the majority of these metronomes. Working on this one. So we're pretty close to resonance right now.
As the metronomes achieve resonance, it's important to notice how the platform shakes.
Now, it doesn't have to just be the force that's being transmitted by the plastic platform. It could be a force at a great distance, for example, the force of gravity. Just these small, little, seemingly insignificant pushes building up over multiple cycles can have dramatic energy transfer. That is how planets do it.
Like the metronomes, the two gas giants form a resonance.
We don't know exactly how long that took, but we have some fiducial marks for timing in the solar system formation, and that means that the grand tack had to have occurred relatively quickly, talking hundreds of thousands of years, perhaps, to a million years.
The two planets retreat until they reach their current positions. The sequence of planets as we find them today is based on Jupiter and Saturn's orbits. The planets eventually achieve a sequencing that many students learn through a mnemonic, such as, "My very educated mother just served us 9 pizzas."
Was there a time when the mnemonic was scrambled? Seems very likely the answer is yes, not to mention a lot of additional letters were probably in there as well.
Jupiter's menace of the inner solar system is finally over.
If Saturn had not formed at the right time and the sufficient size, Jupiter would have continued migrating in, throwing out objects, unfortunate objects in the inner solar system, and ending up very close to the Sun where it would stay. Yes, the Earth would be gone. Or the Earth would have had a terrifying encounter with Jupiter and would have had its orbit changed dramatically to gosh knows what.
There is mounting evidence that Earth had a terrifying visitor. Not Jupiter,
Theia was this planetary body that was roughly the size of Mars.
very body. Theia ceases to exist. Its remains are absorbed by the Earth and intermingled with the debris field. A new planetary body is formed, the Moon. Further evidence is found in rock samples from the Apollo moon landings.
This is a sample from the Moon, if you can see it. This was collected by the Apollo 15 mission.
Moon rocks contain isotopes identical to those found on Earth. When the Moon arose, it is first covered with a magma ocean.
People imagine the lunar magma ocean to be like this magmatic chamber I am describing, but at the surface and covering a whole planet. I see it as this ocean, like the Pacific, but this has to be like completely magmatic, orange, and like probably like fluxing around and probably moving.
Conditions in the lunar magma are as hellish as we can imagine. But a microscopic treasure forms in the magma: crystal zircons. These are the same gemstones used in jewelry. But the zircons in the Apollo moon rocks yield a different treasure.
So those zircon are very important because we know they crystallize in this lunar magma ocean. We know roughly when they crystallize in the lunar magma ocean. So they are one of these old pieces of the moon that we are looking for, one of these old pieces that we can use to date the origin of the moon.
Zircons not only give the age of the moon, they set a specific date for the collision.
The age of the moon is 4.51 billion years old.
4.51 billion years ago, Theia becomes part of Earth and forms the Moon. But the story is not over. Space probes measure the Moon slipping 3.8 centimeters further away each year. One day, the Moon will break free. When that day comes, there will be no more tides, no more romantic moonlit nights. Could planetary orbits be inherently unstable? Could the chaos of planetary migration return? Haute-Provence Observatory, France. It's here that a discovery from a faraway star gives one of the biggest revelations about our own solar system. The story begins when Swiss astronomers Didier Queloz and Michel Mayor noticed something unusual about a star 50 light-years away in the constellation of Pegasus. Everything about this star is ordinary. A main-sequence mid-life yellow dwarf, just like our Sun, but with one strange difference. The star at Pegasus 51 is rocking back and forth. It's a weird anomaly astronomers have never seen before. They check their instruments. Everything is working, including their new spectrograph, a device that splits the starlight from Pegasus into rainbow colors. Hidden inside the colors are patterns of lines. By tracking the day-to-day movement of these lines, astronomers make a startling discovery. Pegasus 51 has a planet. But no one has ever seen a world like this. It's half the mass of Jupiter, yet it's extremely close to its star. 9 times closer than Mercury is to the Sun. The planet at 51 Pegasus must be inside the corona, broiling in temperatures over 1,000,000 degrees Fahrenheit. Soon, another planet is found around another star, and then another, and another. Astronomers have now confirmed over 3,700 exoplanets beyond our solar system. Nearly all of them are Jupiter-class planets grazing their host star. They're a new, previously unknown type called hot Jupiters. They're so numerous, hot Jupiters challenge theories about the origins of planetary systems.
It's very difficult to make a planet close to the star because there isn't enough mass to build a giant planet very close to the star, and there's gravitational frustrations for trying to build a planet very close to the star.
Astronomy is shaken with a new revelation. Planets do not stay put where they're born. When they're big enough, they migrate. It's a process called planetary migration. And yet, our own solar system has no hot Jupiter. Astronomers realize the Jupiter in our solar system was once on the move as well, but its migration was halted by a resonance with Saturn. Pegasus 51 shows where a planet lands when its migration is not blocked. The strongest evidence for the Grand Tack hypothesis comes not from our solar system, but from exoworlds charted around other stars.
Planetary migration is a universal concept. We see evidence of it out there in extrasolar planets, other solar systems. There's no reason why planet migration shouldn't have operated in our own solar system.
The New Horizons probe finds evidence for roving planets within our solar system. While charting ancient craters on Pluto and on the surfaces of its moons, the science team discovered many craters are the same age. This suggests that they were formed by a single event. Even way out here, tiny Pluto was smashed by a wandering planet. The Pluto catastrophe may be related to other planetary migrations in the outer solar system.
It was noticed that the exact orbits of the giant planets, particularly the outer giant planets, the icy planets, Uranus and Neptune, can be explained by their migration outward. There's a point in time about 3.8 billion years ago where Uranus and Neptune trade. And it's because of what some of these mean motion resonance interactions that we were talking about earlier. So this mean motion resonance involving Jupiter and Saturn and so forth just causes all heck to break out in the solar system. Uranus and Neptune, all of a sudden at 3.8 billion years, they literally swap places, and all that debris in the outer solar system gets flung inward towards the inner solar system.
The disruption in the outer solar system causes a new wave of violence. Astronomers call this epoch the Late Heavy Bombardment. Much of the cratering we see on our moon today is from this period. It may be possible that swapping orbits with Uranus is how Neptune got its moon. Today, the epoch of planetary migration appears to be over. The solar system seems stable, but what does the future hold? Computer simulations reveal what may be the greatest threat to the solar system in over 4 billion years. It comes from a very special relationship between Jupiter and Mercury. Mercury's orbit is slowly perturbed, thanks to a subtle but constant gravitational nudge from Jupiter. A new resonance, like the one between Saturn and Jupiter that saved the inner solar system, is forming between Jupiter and Mercury. In 2001, computer models for the solar system were run 2,500 times.
They plug in the positions and the orbits of all the planets in the solar system in a computer, and they just let it run through time, through millions of years, hundreds of millions of years, billions of years, to find out whether or not these orbits are stable.
Change the location of one planet, say Mercury, by 1 millimeter, and you find that that change will give completely different predictions about where everything is going to be millions of years in the future.
To see how quickly and easily things can change, we have only to go back to our metronomes.
All I have to do is stop this platform from moving so that it cannot swing freely. Now, there's no way for the metronomes to influence each other. They're good metronomes, but they're not perfect. They can't be going at exactly the same frequency in the same phase, and they're just going to fall apart because they have no way of forcing the others to go to resonance.
The same applies to planets. Any small change can disrupt their harmony or restore it.
Now that the platform is free to swing again, it can again transfer energy and sync them up just like we saw the first time.
Scientists want to understand the consequences of a destabilized planet Mercury. In one case, Mercury leaves the solar system. The loss of its gravitational pull disrupts the balance of both Venus and the Earth. Earth and Venus swap orbits. The superheated atmosphere of Venus cools. Massive rains pour onto the face of the desert planet. Oceans arise. The land cools. And the air thins. Even the remains of an ancient visitor begin to cool off. Venus becomes like Earth, But the reverse happens to the Earth. As Earth settles into Venus's orbit, temperatures rise. The air becomes unbreathable. Glaciers melt. Oceans boil. The sun looms larger in the sky, only to be obscured by a thickening cloud cover. Suffering will be great, but brief. The entire 4 billion year pageant of life is cooked in a matter of days.
Complete and utter destruction and elimination of all life on Earth. I'm not just talking about higher life, I'm not just talking about civilization, but everything, a sterilization of the planet, is something that I would want to think about a bit.
Sterilized, uninhabitable, and quiet. Just as Theia did 4 billion years ago. The question is, could it happen today? Or is it a fate far away in the future? At a time when mankind itself is but a distant memory?
The problem is that even with a perfect computer that understands all of the laws of motion perfectly, not just gravity, but all the other subtle forces that go into it, you cannot give it accurate enough initial information about the locations, the masses, the sizes, the speeds of all of the objects in the solar system.
Odds are, we may never see such a calamity. And yet, among the billions of stars in our galaxy, how many worlds are on the move? How many will share this fate?
In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out. Communication streams were cut. Airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives, our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
One, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood, The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun. If we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, it is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the sun is the most important thing in the solar system. It meant that we really should understand the sun.
Our sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our sun and our solar system is really the debris from many generations of stars.
The sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the sun shines, it releases the same amount of energy as 1 million H-bombs. The sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the sun. Eventually, they reach the volatile outer layers of our nearest star.
The sun's outer parts consist of 3 regions. There's the photosphere, or surface of the sun, and it's not really a hard surface like that of the Earth. The sun is gaseous throughout. And the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere, and it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The sun produces a continuous outward flow of energy called the solar wind. Constantly blowing, it carries energy out into the solar system, extending our sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the sun, its gravity holds and pulls everything in. Take comets. All comets orbit the sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away. And then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the sun.
A total solar eclipse occurs when, from our perspective, the moon is exactly aligned with the sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, you can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all of the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit. And the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there, the temperatures are so high that protons' hydrogen nuclei can come together, grab each other, fuse, eventually into helium, and in this way, release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, And at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually the same sort of thing that happens with a rubber band, it pops. And when the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode, which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, heating occurs.
It's this heat, delivered to the corona, that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or 1 year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible on the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares and coronal mass ejections.
Increases in solar activity enhance the connection between sun and Earth. Energy expelled from the sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the sun affects the Earth. And that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the sun, coming from a very small localized region of the sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the sun, expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on SOHO.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field, and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a super flare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with the unaided eye, And in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. 2 stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma-ray burst.
Now, one of these 2 stars is a very massive star that might someday form a gamma-ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma-ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma-ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma-ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed, and even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life on near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now, that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion, the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. That makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have 2 types of shields that protect us.
But that could change when WR-104 emits its gamma-ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold, the Sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The sun drives everything on the Earth. The sun is the energy source of the Earth. So all of the energy that's given off by the sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. Basically the sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the sun. But our increased use of fossil fuels seems to be upsetting the balance between the sun and the earth.
Since all living material gets its energy initially from the sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will change the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our sun. Right now, our ozone layer prevents the majority of the sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here, too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between sun and earth that allows life to thrive will require using less of the sun's ancient energy and more of the energy it delivers on a daily basis. After all, the sun's energy output is estimated to be 386 billion megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the earth, and even humankind all come from one place: stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun. And it won't produce any new energy through nuclear reactions, because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star, and it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp. The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able by that time to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will in some part live on. The stardust that gave Earth and all of its inhabitants life will one day be
to get from one end of the solar system to the other by driving. Because space is so huge, we're bringing it down to Earth by scaling the distances in our solar system down to the size of the continental United States and placing the planets along our route. It's a 3.6 billion mile road trip, shrunk down to under 3,000 miles. My name's Colonel Chris Hadfield. When I was 9 years old, I saw the impossible happen. And from that moment forward, I wanted to make the impossible happen for me and to turn myself into an astronaut.
We have booster ignition and liftoff of the Space Shuttle Endeavour.
I've been a mission specialist on a space shuttle, the commander of the International Space Station. All told, I've logged almost 4,000 hours in space. I've flown through it, I've walked in it, I've even sung in it. But now I'm driving it.
Our road trip across the solar system starts here on Long Island, New York. That's the sun off the northeast coast. It's 10,000 degrees Fahrenheit on the surface. That's like 40 times hotter than my NASA spacesuit was designed for. But I'm going somewhere a little bit cooler.
On this journey, I'll be joined by some amazing people, riding shotgun and guiding my adventures.
So it's time to pick up my first passenger. Come on in. How are you? How are you? It's world-renowned astrophysicist Michio Kaku of the City University of New York.
That's right. I've heard so much about you.
I've heard lots about you as well.
You serenade the masses from outer space, right?
And I've been watching all the stuff you've been doing from afar. I think it's nice to have a little look at the world and the universe together.
Grand tour of the solar system.
The first leg of my journey will take us through the inner solar system to Mars. Mars has always held a grip on my imagination. And we're getting tantalizingly close to the day when an astronaut will actually step down onto the red planet. But there are many other wonders along the road from the sun.
Look, there it is. Mercury, the first planet from the sun.
Mercury is an average of 36 million miles from the sun. But here in the miniverse, it's just 24 miles down the road. It looks a little like the moon, which is a place I've always wanted to go.
Many people think that, well, being on Mercury is very similar to being on the moon. No. If you were an astronaut, the sun is this huge fireball lighting up the sky, dominating everything you see around you. It would be quite a hostile environment with the sun just literally staring you in the face.
Yeah.
And it's blisteringly hot on the surface. It's 800 degrees Fahrenheit.
Wow.
Imagine you being able to bake a pizza in your back porch without an oven. But Mercury also has some surprises. You realize that there's ice on Mercury?
Like water ice?
Water ice, right. It turns out if you go to the poles, the North Pole and the South Pole, and look at the bottom of craters where you have permanent shadows, we think there's evidence of water ice.
So even that close to the sun, there are places that are permanently in the dark.
That's right. This shocked a lot of scientists who have this image of Mercury being this hellhole.
Beyond Mercury, we chart a course for Venus. In the universe, it's about 31 million miles, which means in the miniverse, Venus is only about 20 miles away. Venus and the Earth are almost the same size. For a long time, astronomers thought Venus was a kind of twin sister to our planet, but apparently it's Earth's evil twin.
You know, when I was a kid, I read science fiction novels that said that astronauts of the future will vacation on Venus. They'll have tropical environments and swim in the oceans of Venus. Boy, were they wrong.
Tropical environments, I think that was a bit of an understatement.
Temperatures approach 900 degrees on the surface of Venus.
Hotter than Mercury.
Yeah, and it rains sulfuric acid, and the atmosphere is so thick. The pressure is so great on the surface of Venus, it's like being half a mile underneath the water in the ocean.
So that's like being way, way underwater with the pressure of the water all around you.
Yeah, even submarines. Submarines would be crushed like an eggshell at that depth. You know, here on the planet Earth, we experience pressure on our skin, 15 pounds per square inch of your skin. On Venus, it's 1,500 pounds of pressure per square inch.
So it's sort of like in a spaceship when the engine's light and you're crushed back in your chair, except it's crushing you from all directions, not just from one side.
Right. So if you're an astronaut walking on Venus, you'd be crushed like an eggshell. I make a great tour guide, huh?
Maybe not such a good salesman, though. I'm not sure. You should not be selling real estate on Venus.
I'm selling Mars, actually.
Ah, here we are.
Who would have thought that this jewel hanging there in the sky is bright because of sulfuric acid droplets?
And yet we've built spaceships that have made it all the way to the surface, right?
Just for a few minutes, and then they got fried.
So it's the hottest planet in the solar system, and sulfuric acid is raining from the sky.
That's right. So if I was a tour guide, I'd say, maybe we should skip Venus this year.
As we leave Venus, we're headed for the only planet I've actually orbited as an astronaut. And the inner planets are so close to each other that to get there, we still won't be leaving Long Island.
I think you're going to recognize our next destination.
It's terra firma. It's our home world.
Home sweet home.
Yeah. We take it for granted, right?
Yeah.
But most of the universe is quite hostile. All these planets that are blisteringly hot or freezing cold, it's great to find one that's just right to have life on it.
And there's my old home away from home, the International Space Station. I spent 5 months there, taking in the view every single moment I could.
And look, you can also see the northern lights and the southern lights.
Beautiful. I've had the great privilege of seeing the aurora in a way only a handful of people have.
I was outside on a spacewalk. It was on the dark side of the Earth.
Of course, I was just by happenstance, just outside doing a spacewalk.
I had my lights shut off, my eyes had adjusted to the darkness, and we went into the southern lights, the aurora australis. They were rippling between my legs and pouring by. They're mostly like green and red, as you've seen in the pictures, but in them you get all the little subtle colors as well. I couldn't convince myself that even though I knew it was real, it was just hard to somehow accept the fact that this amount of gorgeous, pulsating light and color could be a natural, real thing. It was one of the most magnificent experiences of my life. Plus, we're going 5 miles a second, so it's almost like if you watch the surf crashing on the shore, but then you're skimming through it on a board, so you get your own added speed, like a surfer on a wave. Makes it even more magnificent. It's just...
Well, gee, that's the title of your next book, Surfing on the Aurora.
Maybe you're a better travel agent than I thought. Surf the Aurora. I like it.
Well, I've left Earth before, and I'm doing it again. And this is a journey I've dreamed about many times. from Earth to Mars. A world that has the best chance of becoming humanity's next home. Even when Mars is closest to us in its orbit, traveling there in a spaceship will take between 6 and 9 months. In the miniverse, it's just down the Brooklyn-Queens Expressway. Sounds like a quick trip, but in the miniverse, we have to deal with rush hour.
So how soon do you think until it's not just robots going there, but people?
Well, you know, going to the moon was a piece of cake. 3 days.
There are
you're
people
on the
that would
moon.
disagree with you.
Everything's relative.
Yeah.
To go to Mars, let's face it, it takes months.
Yeah.
NASA's laid out a tentative timetable. We're talking about the 2030s, just to orbit around the red planet, and perhaps by 2040 actually landing on there.
Wow.
Unless, of course, private enterprise catches up, in which case we'll be on Mars even sooner.
Yeah.
Would you want to go to Mars?
Oh, absolutely. Yeah, in a heartbeat. I'd love to. The idea of that early exploration and discovery, that's what always has made my heart beat faster, yeah. If it were easy, I don't think I'd really want to go, but the challenge that makes it possible, to me, that is what really makes me want to go.
But for me, nah, I don't think so. First of all, being a physicist, I know the odds of success. 1% of the spacecraft will blow up and never reach Mars.
Sounds like physicists are pessimists to me.
No, realists, that's all. It's just realists.
But that means 99% of them make it, you know? I think Mars is worth the drive. So if I sign up to go to Mars, if I stick my hand up way high and get picked, what do you see as the biggest hazards between here and there? Is it getting hit by small meteorites? Is it the radiation?
I think it's all of the above. Yeah. Especially radiation. Radiation from the sun, cosmic rays. Radiation causes premature aging. At best, your body will age faster than normal. Yeah. And at worst, cancer.
You know, something else, having spent half a year in space, one of the beauties of being on the International Space Station is you got the world in your window all the time. But as soon as we turn tail to Earth, fire the engines, and start going to Mars, within a week or two, Earth is just a little dot, and you have nothing out the window for 6 months, 9 months, however long it takes. I think you can't play down the psychological effect of that.
Right. So my attitude is, let someone else get all the ticker tape parades.
Despite all the challenges, Mars pulls at my imagination. It's a place where humanity has long hoped to find the first signs of alien life.
For the most part, we see no evidence of life whatsoever. You know, some people think they see a face on Mars, and there's one formation that looks like Kermit the Frog, actually, on Mars.
I haven't seen the Kermit the Frog formation.
But they're optical illusions.
There's evidence of methane in the atmosphere, which can come from microorganisms, but doesn't have to. Traces of water might bubble up to the surface, but might be too salty to support life. But there's also water in the ice at the poles.
Journalists say follow the money. Yeah. Physicists and astronomers say follow the water.
Follow the water.
Where there's water, there could be hydrocarbons, organic chemicals, and who knows, maybe even an alien form of DNA. Wow, you can really see Mars in its full glory. I mean, you can see why the ancients named it after Mars, the god of war, because it's so red.
Red like blood.
Or like rust.
Or like the bridge, right?
That's
Rusty,
right.
like the bridge.
Sometimes that rust in the soil gets kicked up by the Martian wind. So if I was standing on the surface, the sky would be pink, not blue.
You know what amazes me is to think that right now on Earth there are a few people in darkened rooms operating controls that are driving robots around on that planet right now. And that maybe not too long from now, people will have a chance to go all the way there actually in person.
There'd be many wonders to behold on the surface of Mars, but the one I want to see most is Olympus Mons. It's the biggest mountain on any planet in the solar system.
It would extend from here, New York City, all the way into Canada.
And how high?
It would be like, well, take 53 of those Freedom Towers going all the way up.
53 of those? Wow.
Yeah, imagine 53 of them stacked vertically on top of each other.
Wow, that's
53 of
out
them.
of sight, wouldn't it?
That's 16 miles high, 3 times taller than Mount Everest.
And you don't want to be the astronaut that plants the flag on the top of Olympus Mons there?
No, I'll let someone else have the glory. But that's the lure of Mars.
As I drive Michio back to his home in the city, I wonder what home would look like on Mars.
So instead of building a dome like in science fiction novels, why not use the volcano tubes that already exist? Tubes that once had liquid lava flowing through them can also be used as caves for the astronauts, protected from the cosmic rays, the solar flares, and the micrometeorites. That'd be the quick and dirty way to get a Mars base off the ground.
It was an absolute delight, Professor, to travel the inner solar system with you.
Right? It's been a cosmic tour to the universe.
Thanks. I look forward to seeing you somewhere else around the solar system.
We covered 141 million miles in the solar system without ever leaving New York. But that's about to change. Like a pioneer pushing into a vast, uncharted wilderness, I'm ready to leave the familiar surroundings of the inner solar system for the strange and mysterious realm of the outer planets.
In other words, I'm headed to Philadelphia.
In the inner solar system, we passed 4 planets in less than 100 miles. Things are going to get a lot more spaced out. In the universe, the average distance between the Sun and Mars is 141 million miles. Then, the average distance from Mars to Jupiter is 342 million miles. In the miniverse, that's like a trip from New York to Washington, D.C.
Whoa! Halfway between Mars and Jupiter, there's an enormous ring of rocks called the asteroid belt. That one just missed. Yikes. The asteroid belt has millions of small particles.
It also has about 750,000 bigger asteroids, some of them more than 3,000 feet across. Some people think that the asteroid belt looks like the world's most dangerous video game.
But in real life, there's an average of about 600,000 miles between each of the significant asteroids.
Even in the miniverse, that's about a quarter of a mile. Still, plenty of space to maneuver through safely. So I've made it to Philadelphia in one piece. As I head for the outer planets, I'll need a guide who really knows this part of the solar system.
Hey, come on aboard.
Why, thank you.
It is the chief astronomer and planetarium director of the Franklin Institute in Philadelphia, Mr. Derek Pitts.
You got
Welcome
it.
to my spaceship.
How are you, Chris? Thanks a lot.
Ready. Are you ready to head across the solar system with me?
I'm ready to take a trip through the planets.
All right. So we got some big planets coming. Glad to have you aboard.
I'm looking forward to it. This is the first time I've actually taken a trip through the outer solar system.
Well, there's a first time for everything. So the beauty of shrinking the whole solar system down to the size of the U.S. is you get through the asteroid belt fairly quickly.
We're on the road to Washington, D.C. Drawn in by the immense gravitational pull of the most massive planet in the solar system. Jupiter's almost 88,000 miles in diameter. That's 1,300 times bigger than Earth. You could actually fit Earth and all the other planets inside Jupiter and still have room.
And in fact, Jupiter itself weighs more than all the other planets of the solar system put together twice.
Wow. It's the heavyweight.
It is big.
Jupiter's huge, but even with all that mass, there's no place for an astronaut to put a footprint.
It's really just a big, big ball of gas.
Wow.
Hydrogen, helium, methane, ammonia.
Wow.
But as an astronaut, what would it look like to take my spacecraft and start diving down into Jupiter?
You'd have a very interesting trip as you descended down into the clouds of Jupiter. First of all, you'd start down into the cloud tops of maybe several thousand miles. You'd start to notice that you're losing sunlight and things are getting darker. But you'd begin to pick up lightning. You'd see flashes all around you.
If you get right to the very center of Jupiter, what's right there in the middle?
Well, oh my gosh, the pressure increases so much that gaseous hydrogen can be squished down until it becomes a liquid, and then it turns into something very interesting called liquid metallic hydrogen.
Liquid metallic hydrogen. That sounds like a science fiction movie.
I wish I could explain it, but I don't think I
know
can
that
even
creature
tell you what
that
it's like.
drags himself up out of that
Out
silver
of the
liquid.
ooze and
That sounds like liquid metallic
I think
hydrogen.
that's where
to
that
me.
guy came from.
Yeah,
Well, in any case, right down in the middle of all this liquid metallic hydrogen, there might be a rocky core, a solid core inside that.
So if you get right to the core of Jupiter, I mean, what sort of pressure are you actually facing there?
All right, so the pressure at the core of Jupiter is about 30 million times the surface pressure here on the Earth. So if you start at about 6 feet tall, by the time you get to the center of Jupiter, you're going to be about a half an inch tall. But you also have extremely high temperature down there as well, about 63,000 degrees Fahrenheit. About 6 times hotter than the surface of the sun. So if you're an astronaut going into this, you're going to have a beautiful light show for the first half of your trip. And then the next half of your trip is going to be like the worst horror show nightmare you've ever experienced.
Wow. Yeah, I'm going to have to really rethink my my Jupiter spacesuit.
I think you might want to go with the space probe thing instead.
Yeah.
Okay, so maybe it's safer to let spacecraft like the Juno probe go inside Jupiter.
Great. Approaching Jupiter.
But to orbit Jupiter, to see it up close, would be one of the most amazing experiences in the solar system.
Whoa. Look at that, right above the... Holy cow.
You know, I knew it was big, Chris, but this is really incredible.
Look at the colors of that. That's amazing.
And look at the detail you can see in the cloud tops.
Wow.
All the little whirlpools.
That's worth the trip.
It is definitely worth the trip.
It makes sense that Jupiter's over Washington, D.C. Washington's influence is felt all over the world, just like Jupiter's influence has been felt all across the solar system. Its gravitational pull is so strong, it acts like a cosmic vacuum cleaner, sucking in comets and asteroids that might otherwise rocket into the inner solar system and strike our planet. As an explorer, I'm often drawn to the things that frighten me the most. On Jupiter, it's the intense violence of the monstrous Great Red Spot.
Whoa. That's incredible. And the red spot right over here coming across this way.
It's a ferocious storm that may have been churning for 300 years.
It's really spectacular.
If I could orbit Jupiter at the same altitude that the space station orbits our planet, the Great Red Spot would fill my entire field of view. It's just that big, larger than the whole Earth.
That's a view and a half.
That really is amazing.
I flew through a lot of bad weather when I was a fighter pilot. I wonder what it would be like to drive through the Great Red Spot.
Are you serious?
Yeah.
That's an awfully dangerous thing to do.
The center is relatively calm, but as you near the outer edge, the winds climb to 400 miles per hour, twice as fast as the worst hurricane winds on Earth.
Okay, when you're flying through the Great Red Spot of Jupiter, remember, keep your windows up and your air conditioning on.
And that's because the red spot is full of ammonia and ammonium sulfite. Not good stuff.
Not good.
As we speed away from Jupiter, I'm reminded of the Cassini spacecraft that visited here in the year 2000. It sent back some unforgettable images before using Jupiter's gravity to slingshot towards its ultimate destination, Saturn. I've been lucky to see many spectacular sights in my time as an astronaut, but I've always thought that nothing would be more stunning than to see the rings of Saturn up close with my own eyes. It took the Cassini probe more than 3 years to make the trip from Jupiter to Saturn. But in the miniverse, Saturn's just 6 hours away in West Virginia.
Got a bit of road to cover between now and then.
And it looks like we won't get to Saturn till after dark. Good thing we space explorers always pack snacks.
Well, look.
Look at that.
We got some astronaut ice cream.
Oh, my favorite.
How's that? Let's try some of this.
Can I have a piece?
Sure. Let me give you a hunk
It's
there. There we go.
The attractive color you'd hope your space food would be.
Cheers.
Cheers.
It's not as bad as I thought it was going to be.
So I do have to fess up, though, we do not have astronaut ice cream on the space station. It tastes nice, but it's just too crumbly and not practical for weightlessness. Right. There's going to be stuff in your nose, in your eyes, in the computers.
This would be a mess everywhere.
Not bad for the miniverse, though.
No, it's good for the miniverse.
So let's just talk about the planet itself. You're an astronomer. What can I expect when I get to Saturn?
It's the rings.
It's got rings.
Everybody loves the rings.
Yeah.
All the gas giants have rings, but none of them can match Saturn's.
If you're measuring about 176,000 miles across.
That's wide enough to line up 22 Earths side by side.
If you were flying your spaceship right next to the rings, what do you think it'd look like up close?
If you're right up close on it, it really would look like a very well organized rubble field because you have these particles of different sizes. You know, you're down to something that is dust sized and maybe up to objects that are the size of a small car or even a small house, but they're all in there together.
From just a little distance, the rings don't look like a rubble field at all.
Wow. Look right there.
That is spectacular.
Wow, you can see everything. You can see the colors and the delicate swirls and the rings.
The rings really are spectacular. Oh my gosh.
Saturn has dozens of moons, and at least 3 of them have underground oceans. Those are Dione, Enceladus, and Saturn's biggest moon, Titan. For a moon, Titan is pretty titanic. Even bigger than the planet Mercury.
Titan's really a wonderful place to visit too, because it's the one place in the solar system that we know of that has oceans on the surface.
Titan has oceans of what?
Ah, there's the catch. A lot of it is methane that's actually out on the surface, pooling in lakes. It also has a cloud cover that actually rains methane down onto the surface.
Wow, so methane rain.
At about 300 degrees below zero.
Oh, wow. So, you know, the suit that I wore for my spacewalks, I'm not sure that it could put up with the huge temperature extremes that we're seeing on the moons of Saturn.
You need something really special.
I don't think thick socks are going to help.
You need a little bit more than that.
You know, sleeping on a space station, you dream about views like this. When you close your eyes sleeping on a spaceship, sometimes you see flashes of light with your eyes closed. It's the radiation and the high energy particles from the universe that are going through your optic nerve and making your vision flash. It's a real reminder of that you are somewhere other than Earth.
You don't see this on Earth, do you?
No, because our atmosphere soaks up the little particles that cause this to happen in our eyes. And I can imagine the first astronaut, the very first one who saw that, is probably going, I don't think I want to tell anybody. I'm seeing flashes when I close. I could see two astronauts going, hey, do you see flashes?
See anything like that? So
well, yeah, oh, we all do. Oh, okay.
That's a really special experience.
It's part of what astronauts dream about.
I hate to leave, but I have more planets to visit. And Derek's got to get back to Philadelphia. Time to part ways.
Chris, it's been great.
It has been wonderful touring the solar system with you.
Thank you so much for taking me around. I've had a great time seeing all these planets so close.
I got a little bit more of the solar system to see, but thanks for being a tour guide
So
for
look,
me.
you have a really great trip.
Safe travels home, sir.
All right, Chris, take care now.
All right, bye. Gonna ride that lightning one more time. I'm gonna ride that lightning one more time. I'm gonna ride it one more time, 'cause there ain't no finish line. I'm gonna ride that lightning one more time.
Out beyond Saturn, just like on the road through America's heartland, it can look pretty empty. Gives you a lot of time to think and look.
When I was a fighter pilot flying F-18s in the subarctic, I loved to take the airplane up as high as air traffic control would let me. And then I'd engage the autopilot, sort of like I could engage the cruise control in this car. And then I would shut off all the lights in the cockpit so that it was completely dark. And then I would let my eyes adjust. And you could start to see the stars as your eyes opened up. And for me, that was sort of an early taste of what spaceflight was going to be like, as close as I could get to the heavens, but almost no barrier at all between me and the rest of everything else. My first small step into space. If we were making this trip 300 years ago, it would have been in like a horse and carriage, we would have stopped at Saturn, because as far as everybody knew, that was the last planet. It was the furthest planet that we could see with the naked eye.
But there is another planet down that road in front of me. Another giant of gas and ice. Uranus. From a distance, it's hard to imagine the violence going on there. These Midwestern flatlands can get hit by 200-mile-an-hour tornadoes, but if I flew a spaceship into the clouds of Uranus, I'd be fighting winds up to 560 miles an hour. And as you get closer, you start to see something very strange. Uranus is lying on its side.
So if you were the Space Transportation Safety Inspector, you'd look at this and say, what the heck happened here?
Something in the early solar system, possibly some rogue planets, knocked this giant world over, rings and all. And that might not have been the most incredible thing to happen to Uranus. About 4 billion years ago, it was ripped out of its orbit. Gravitational interference from Jupiter and Saturn made Uranus switch places around the Sun with Neptune. That's like Kansas swapping locations with Colorado, but it happened. So today, Neptune is 1 billion miles out from Uranus, which puts the 8th planet in western Colorado. Like the pioneers of old, I've reached the Rocky Mountains. Ahead lies my final frontier. And here's my final co-pilot.
Hello.
Hello,
How you
Commander
doing?
Hadfield. Nice to meet you.
It is great to meet Dr. Laura Danley, astronomer and curator of the Griffith Observatory in Los Angeles. Welcome to my spaceship.
Thank you.
We have the privilege of traveling a little bit of the solar system together.
I'm really looking forward to it.
Yeah, some
We've got
things
a
to...
long distance to travel.
Let's
go.
Let's go. Seat belts.
All right.
Engage.
So, Laura, as my spaceship enters into orbit around Neptune, what's the first thing I would notice?
Well, Neptune is blue, and there's nothing you can do.
That'd be a good song, wouldn't it?
That would. Maybe you could sing it later.
Looking down on Earth from the space station, you're struck by the incredible deep blueness of our planet. But the blue on Neptune isn't water. It's reflected light from methane in the atmosphere. And that atmosphere is roiled by the wildest winds in the whole solar system.
There are storms in the atmosphere that appear quite dark.
Like spinning storms?
Yeah, huge cyclones.
Huge cyclones.
And they are so violent that the wind speeds in those are about 1,500 miles an hour.
Like 1,500?
1,500
I mean,
miles
a
an hour.
category, whatever, hurricane, 200 miles an hour is wicked.
Yeah,
on the
this
Earth.
is a category 25. It's
Wow.
way up there.
How big is the storm?
The big one is about the size of the whole Earth. You could fit a whole Earth in it. Yeah, it makes our storms look like kindergarten over here.
Earth-sized storms with winds 10 times faster than my top speed.
Wow, that's incredible.
Yes.
And look at that.
Oh, here we are. Wow. What an amazing sight.
An astronaut visiting Neptune wouldn't want to leave orbit because there's nowhere to stand and plant your flag.
No, you can't be standing on it because it's gas mainly.
Sure.
So you would keep falling on through.
Whoa! Here's some solid ground. Neptune's largest moon, Triton.
Wow.
Triton is an amazing world. First of all, it's about 1,500 miles across.
Standing on Triton, what do I see? What's it look like?
Well, an icy surface everywhere. Mainly nitrogen, little methane, maybe a little CO2. If you're standing in the right place, you might also see kind of an orangey, rust-colored coating on it. These are hydrocarbons or organic molecules like methane and ethane that have been singed by ultraviolet light from the sun, and they fall down onto the surface like just a fine veneer on top. And if you were in the right place, then you may see a geyser of nitrogen ice spewing into space.
An ice geyser spewing up around me, wow.
5 miles tall. Think about that compared to, say, Old Faithful.
Miles high.
Right.
Well, I want to go.
It's an amazing world.
Sounds like it'd be worth the trip.
Yeah.
Triton may have something special that makes it a target for future explorers. A warm subsurface ocean with the possibility of life. Think how amazing it would be to gaze from a scenic overlook on a distant world and see someone or something looking back at you.
You pulling the shuttle?
Not very many, 3. Shuttle's pretty low G vehicle.
Think you can get us 3G? Why does everybody know about fighting the Gorn? That is like one of those memorable... The Gorn was such a wonderful monster.
From Earth, even the Hubble telescope can barely make Pluto out. That's because it's an average of 3.6 billion miles away.
If you were able to fly out there in the shuttle, it would take you about 20 years.
A long time with 7 people sharing one toilet. That'd be a while.
And then if we were driving at 60 miles an hour, it would take us 6,700 years to get out there.
Wow.
So, yeah.
Are we there yet?
In 2006, by sea, as the New Horizons probe sent back one
It's just going to be an icy chunk out there.
Yeah, like an ice cube.
Yeah, surpassed everyone's wildest imagination.
Turns out, if I went to Pluto, I'd find a world with a super thin atmosphere that, like Earth's, is mostly nitrogen. A world with mountains of solid ice, 11,000 feet high. And Pluto has an ice field about 1,000 miles across in the shape of a heart. And deep under its icy surface, a huge, warm, liquid ocean. Nobody thought we'd be following the water to Pluto. We're...
Cool car.
Very cool.
There's a mist rolling in from the Pacific Ocean, which gives me a very slight idea of what a day on Pluto would be like.
40 times farther away from the sun than the Earth.
So the sun shrunk down to almost nothing.
Shrunk down to just a bright star.
Really?
So it's not entirely dark, though. Sort of like it is around dusk here on Earth.
So where should we land? Should we land right in the middle of the heart?
You know, that wouldn't be a bad place to land because it's wide open.
You'd have a nice little smooth spot.
Yeah.
Good for skating.
I was just going to say, you're Canadian. Strap on your skates and head on out.
What sort of gravity does Pluto have?
It's just about 1/15.
1/15?
Of Earth's, and the moon is
Wow.
1/6.
So
you could really jump high.
If you weigh 200 pounds on Earth, you're weighing like 12 pounds on Pluto.
Yeah.
Wow. Be pretty cool.
It'd be very cool.
Actually, it'd be pretty cold.
Every day, we're closer to the time an astronaut from Earth looks out from the porthole of a spacecraft and sees...
There it is, at long last.
Long voyage. Imagine having that in front of your naked eyes.
Still can't get over it has a heart on it.
It's just so poetically perfect.
It is, it really is. It's a beautiful world.
And you know, to have been around the world so many times, you look at the world a lot, but it's when you turn and look what there's still on the other side, what's...
By on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras, and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms, but with our minds, we have learned to follow time's trail out to longer and longer intervals. We know from precise measurements that the Earth goes around the Sun every 365.256366 days. Much of the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. So to glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. With entropy uniformly low, this was the time of the tiny. Subatomic particles like quarks and leptons stirred into a hot soup. They combined into atoms, setting in motion the primordial era. The universe cooled as it ballooned, growing dim and falling into what's known as the cosmic dark ages. After several 100 million years, larger clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars, like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our sun. A distant civilization may scan it for planets, but by then they won't see Earth. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. But a wholesale thinning out of the universe is inevitable in filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this. Not much larger than our planet Jupiter, a red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Brown dwarfs and red dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, they'll be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as their host galaxies grow dim, another process will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around 1 billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the hole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the 3 spatial dimensions, plus time, that we experience in our everyday lives. We may be like an insect living on the 2-dimensional surface of a pond, unaware of the deep and complex reality below it. it may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny 1-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way